Hi, this lesson is about computing the volume of a solid by the cylindrical shell method, sometimes just called shell method. So in order to build our integral, we're going to be using this formula, 2 pi rh, um, because if you think about what a cylinder looks like, could be oriented vertically or horizontally. The top and bottom, if it's vertically oriented, is a circle, and the circumference of that circle is 2 pi r, and the height of that circle is h. So if I want just the shell, in other words, not the inside part, not the volume, then it's the 2 pi r times h. So the challenge will be determining what is your radius and what is your height, as well as the boundaries or your limits when you're determining your volume. So, as I mentioned, you could have your shell oriented vertically, like in this picture, or horizontally in this picture. Since your shell has some depth associated to it, so you can think of it as like very thin pieces of paper that are rolled around this solid infinitely many times, and we're computing 2 pi rh infinitely many times from the beginning to the end of the solid. So when it's oriented vertically, the depth of the height is with respect to x. So you would be integrating with respect to x. So in other words, your radius and your height would have to be in terms of x. When you are oriented horizontally, the depth of your shell would be with respect to y, like in the second picture, and therefore your radius and height would be expressed in terms of y. So just like I mentioned with discs and washers, you're going to want to know how to draw these. So this statement that's here in this green box is important. When you're drawing a representative cylindrical shell in your solid, you want to make sure that you draw the height of the shell parallel to the line that the region is being rotated around. So if you were rotating around the y-axis or a vertical line, it would look like the first picture. If you were rotating around the x-axis or a horizontal line, it would look like the second picture. And remember, the depth, the dx or the dy, determines whether you are integrating with respect to x or y. So that's always important to figure out. So here's a more detailed picture of what cylindrical shell method allows you to compute. So imagine that you had a graph here, f of x, and the area underneath that curve from 0 to a is represented by this space here that I'm shading in. And so imagine rotating that around the y-axis, and that rotation creates a solid. And what you're seeing in these three pictures is a representation of what the cylindrical shell method does. So in the first picture, that vertical strip is the height of a shell, and that height has a depth with respect to the x-axis. Then in the second picture, this one here, imagine pulling that height out of your area and going around through the entire solid, creating this representative shell here in this second picture. This shell has a radius that goes from the line of rotation, your y-axis, to any point on the curve. And so remember, here's your curve. Sure if you can still see it. So that distance is a distance that we're calling r, and r is going to be with respect to x in this example because of this, because of the depth is in terms of x. And the height is, well, that's just going to be your function value. It's whatever the f of x value is on your point. So your height is f of x. And in the last picture, it's a representation of what would happen if you did this cylindrical shell computation infinitely many times. You would basically be starting from one point of the solid through to the endpoint of the solid, and doing this cylindrical shell method infinitely many times would mean that you would be computing the entire volume. So in this example above, if I were to compute this volume, my integral would be from 0 to a. Those are my two limits here. And then it's the formula, remember, is 2 pi RH. The R is the value of x. It's x units to the right from the y-axis, and the height is your function value, f of x. All right, so let's do an actual example here below. We want to find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared about the y-axis. So just like the lesson on area and the lesson with washers, we have to figure out what our boundaries are. So we have to find out where x and x squared intersect. So we set them equal to each other. When you solve, you get 0 and 1 as the common points that they share. And so for the purposes of graphing, you're going to want to know what the y values are. So when x is 0, y is 0. So this is a point of intersection. And when x is 1, y is 1. So that's the other point of intersection. The line is y equals x, which you see here on the graph. So that's this one right here. And the parabola is the one that's below the line. So that's this one right here, x squared. All right, so now that we see the picture, imagine that the area that's shaded in blue gets rotated around the y-axis. And so the rotation creates the solid. And I've created a mirror image here on the left in green. So again, imagine that this is something that you can hold, something that has a front, a back, sides, something, a solid shape. So when I compute my volume by the cylindrical shell method, I need to determine what my radius and my height is. So the radius is the distance from the y-axis to that starting point where the height was drawn. So this is my radius here, and my radius means that I have moved over from left to right x units. So my radius is x, and my height is the difference between the two functions. And so you always want to compute height with the larger y value minus the smaller y value. So when you're drawing your cylindrical shell vertically, the way we are in this picture, you want to subtract your functions where it's the function that's higher up minus the function that's below. So that will be x minus x squared. So now we put that all together in the formula 2 pi RH. So I get the integral from 0 to 1 of 2 pi x times x minus x squared. So before you integrate, you should distribute the x across, x minus x squared, and factor out the 2 pi. So we get this 2 pi times the integral of x squared minus x cubed. Then we take the antiderivative by doing anti-power. So you get 2 pi times 1/3 x cubed minus 1/4 x to the 4th. Then we use the fundamental theorem of calculus, plug in the upper limit minus the lower limit. So you get 2 pi times 1/3 minus 1/4 minus 0, get a common denominator, and simplify, and you find that your volume is pi over 6. All right, so let's do another one. We want to compute the volume of the solid created by rotating the region bounded by y equals e to the negative x squared, x equal to 0, which is the y-axis, which I've shown right here, and x equal to 1, which is this line right here. Okay, and the curve y equals e to the negative x squared from 0 to 1 is just this part here on the right, okay? And the area that we are rotating is the area that I shaded in green. So imagine rotating that around the y-axis so it creates this side over here. And again, there's a front and a back. Imagine this going all the way around, creating this three-dimensional shape. All right, so since I'm rotating around the y-axis, you want to draw the height parallel to the y-axis. So that's the bar that you see here in orange. That depth of that bar is with respect to x, so that's telling me that my limit should be in terms of x, as well as my radius and my height. The radius is the distance from the center to any point, or where that height is, and that, remember, that height will change depending on where you are in the solid. And so that radius is x units, so you move x units to the right, and the height is whatever the function value is, which is e to the negative x squared. So now we put that all together right here. I have the integral from 0 to 1 of 2 pi x e to the negative x squared. So in the next line, I factor out the 2 pi. And notice that here you have to use U-Substitution or the substitution rule, because you have a product, and e to the negative x squared is a composite function, and negative x squared has a relationship with x in terms of derivatives. So a good choice would be to let u equal negative x squared, which is what you see here. Then you take the derivative of or the differential of both sides, so you get du equals negative 2x dx. Remember, you have x dx in your original function, not negative 2x dx. So in order to eliminate the negative 2, you multiply both sides of the differential by negative a half. So I get negative 1/2 du equals x dx. So negative 1/2 du will substitute x dx, and u will substitute the negative x squared that you see here. So before I make that substitution, I need to deal with these limits. Remember, 0 and 1 are with respect to x, but I'm now going to redefine everything in terms of u. So I did that work here. When x is 0, if you plug in 0 here, u is 0. When x is 1 and you plug in to what u is equal to, you get that u is negative 1. So my new limits are from 0 to negative 1. All right, so let's put this all together. I have my volume is equal to 2 pi, the integral from 0 to negative 1 to negative 1, and then negative 1/2 du is the x dx, and e to the negative x squared is e to the u. So I've made my substitution. So now this is a very basic integral to take the antiderivative of. So first I multiplied the negative 1/2 and the 2 pi, so that gives me negative pi times the integral. The antiderivative of e to the u is itself. So when you integrate, you get this, negative pi e to the u, evaluated from 0 to negative 1. Substitute in your upper limit first. So e to the negative 1 is the same as 1 over e, and e to the 0 is the same as 1. So that's why you see that second to last line. And in the last line, I distributed the negative pi and just wrote the positive term first. So negative pi times negative 1 is pi, so that went first. And negative pi times 1 over e is minus pi over e, giving you your volume. Okay, let's do another example. Here we want to compute the region bounded by y equals x minus x squared about the line x equal to 2, and compute the volume of that solid. So this time I'm rotating around a different line, but x equal to 2 is a vertical line. So it will be similar to what we did in the previous two examples where we were rotating around y. But when we rotate around a different line, you're going to have to make an adjustment to your radius. So this function is a parabola. So when you're graphing the parabola, you're going to want to identify the vertex as well as the x-intercepts so that you know what's bounding the parabola. So you want to look at where the parabola is with respect to the x-axis. So first I found the vertex, and I used calculus to do that. So I took the derivative and set it equal to 0 because remember that will give me the maximum point, and the maximum point is the vertex. So you get that x is a half, plug into the original function, and you get y is a fourth. So your vertex is 1/2, 1/4. All right, so that's one point that we'll show on our graph. Now let's find our x-intercepts. X-intercepts are found by letting y equal 0. So take the original function, set it equal to 0, factor, and you get 2 points, 2 x-intercepts, 0, 0, and 1, 1. So those points are reflected here on my graph. in blue. So here's 0, 0. Here is my x-intercept 1, 0. And here's my vertex 1/2, 1/4. I've also shown my line that we are rotating around, x equal to 2 is right here. So imagine taking that area underneath the blue curve, or that part of the parabola, and rotating it around x equal to 2. And so when I do here, I get my reflection across that line. And so again, imagine that this creates a three-dimensional shape with a front and a back and sides that you can hold. And you want to draw your representative shell by drawing your your vertical line parallel to the line x equal to 2 to represent the height, and then taking that height and rotating it around to the reflection here on the other side, and there creates your shell. So it's like a rather short, wide shell. Okay, so now we have to figure out what our radius and our height is. So the distance from here, from the y-axis to here, is 2 units, right? Because we know that that's the line x equal to 2. And the distance from here to where your height starts, or wherever your height is in your solid, well, that's going to be x units. So the radius, this part right here that we're interested in, is 2 minus x. That will give me the radius of the shell. Now I have to figure out the height. Well, the height is this right here. And so that's just the distance from the x-axis to any point on the curve, and that is your parabola x minus x squared. Okay, so now that we know our radius and our height, we have to substitute that into the formula, 2 pi rh. That's what you see here. My integral is going from 0 to 1. That's based on your points of intersection. This is your r, and this is your h. Then you want to do, you want to FOIL that out, do a little bit of algebra before you integrate. When you FOIL, you get the second line. We do not have like terms, so I just copied it down again here in the third line, but factored out 2 pi. And now I'm ready to take the antiderivative, and we're, oh, sorry, you did have like terms, so we combined these right here. And then we're ready to take the antiderivative. So we did anti-power rule. The antiderivative of 2x is x squared. The antiderivative of minus 3x squared is x cubed. And the antiderivative of x cubed is 1/4 x to the 4th. Now we substitute in our limits. Plug in the upper limit minus the lower limit. So you plug in 1 first. When you plug in 0, all the terms go to 0. So you're left with 2 pi times 1/4, which is equal to pi over 2. All right, so here's another, but this time we're going to rotate about the x-axis. So our cylindrical shell is going to be horizontally oriented. So we want to rotate the region bounded by y equal to the square root of x and the line x equal to 4, and revolve it around the x-axis to generate a solid, and then compute the volume. All right, so you're going to want to know where square root of x begins and where that area ends. So square root of x, the domain of the square root of x is from 0 to infinity. So we know we're going to start at 0 and we're going to end at 4 because of this restriction right here. So y equal to 4 is right here. Sorry, x equal to 4. So when x is 4, sorry, your y is 2. So we have the point 42 here. The area that we're rotating around the x-axis is shaded in this reddish pink color. And the rotation is what you see below here in blue, because remember, we're rotating around the x-axis. Because we're rotating around the x-axis, you want to draw your height parallel, which means your height should be drawn horizontally, the way you see here in orange. The depth of this height is with respect to the y-axis, so that means everything should be in terms of y, your limits and your function. And then imagine taking that height and rotating it around the x-axis, so you've created your shell that you see here. Again, the shell has a radius and a height associated with it. The radius is this right here. It's the distance from the x-axis to the point on that height. So that is y units. And the height is this right here. So the way we figure out height is that we know that we have 4 units from the y-axis to x equal to 4. And the distance from the y-axis to any point on the curve, well, that's whatever the function is. Now, keep in mind, your function is expressed in terms of x, but I need it expressed in terms of y. So if you square both sides, you get that x is y squared. So your height is what you see here. It's 4 minus y squared, and that will give you that horizontal bar that I drew inside of the solid. So now that we know the radius and the height, we're ready to build our integral, which is what you see here, 2 pi rh. So I have the integral from 0 to 2. Remember, your limits have to be in terms of y, so that's why I picked 2 here and not 4. And this point here was 0, 0. 2 pi r, and r is y, times your height, which is 4 minus y squared. So factor out the 2 pi in the next line and distribute y across 4 minus y squared. So you are integrating 4y minus y cubed. Do anti-para rule to get the third line. So you get 2 pi times 2y squared minus 1/4 y to the 4th. Substitute in your upper limit minus your lower limit. So you get this line here. And when you do the arithmetic, you get that your volume is 8 pi. All right, here's another. We want to rotate the region bounded by y equal to negative x squared plus 9 when x is greater than or equal to 0 and y equal to 0 about the line y equal to 9 and compute the volume. So once again, we're rotating around a horizontal line, but this time it's not one of the axes. It's the line y equal to 9. So we'll have to make some adjustments here. So here's our picture. We know that we're only interested in values that are greater than or equal to 0 because of this statement here. Negative x squared plus 9 is a downward facing parabola with a vertex at 0, 9. So that's this point here. This is the point 0, 9. And normally you would draw that on the left or in quadrant 2 and 3 as well as quadrant 1 and 4. But we're only interested in values greater than or equal to 0. So that's the graph that I drew here in green to the right. It intersects the x-axis at 3. That's an x-intercept. So that's this point here. So the area that I shaded in green is what gets rotated around this line y equal to 9. And so the rotation I drew above here in blue. So that's what's creating this 3-dimensional solid. Okay, so now I've drawn my height in the original area, in the green area, that is parallel to the line y equal to 4. So that's what you see here. And that height has a depth associated with it with respect to y. Okay, so pull out that height, rotate it around, you create your shell that's horizontally oriented. So now let's figure out what my radius and my height is. So remember, I'm going to be integrating with respect to y. So y equal to negative x squared plus 9 isn't going to be useful. I'm going to have to solve this for x. So the way you do that is subtract 9 from both sides. Multiply both sides by -1, so you get 9 minus y equals x squared. And then take the square root of both sides. You don't need to do plus or minus because we are in the first quadrant, so it's just the positive result. So x is the square root of 9 minus y. Okay, so now that we know that, that means that this height is determined by the point, this value, and so therefore the height is the square root of 9 minus y. And how do we figure out our radius? Well, our radius is the point from the line that you rotated around, to where that height of the shell begins. So my radius is going to be 9 minus y, because from here to there I have 9 units, and from here to there I have y units. So when you subtract, you have the radius that we're interested in. So now that we know radius and height, we can build our integral. And remember, your limit should be in terms of y. So my integral goes from 0 to 9. That's the y coordinate. And it's 2 pi, and this is r, and this is my h dy. So here we can combine the r and the h. They have the same base of 9 minus y. So it's basically 9 minus y times 9 minus y to the 1/2. So you can add the exponents. So we are going to integrate 9 minus y to the 3/2. All right, so again, we need to use U-substitution. It's a pretty basic U-substitution, but it's a composite function, so that's what you see here below. I'm going to let u equal 9 minus y. My du is negative dy, but I don't have a negative dy in my original problem, so I multiply both sides by -1, so negative du will replace or substitute dy. I'm also going to reevaluate my limits. When y is 0, your u is 9. When y is 9, your u is 0. Okay, so now I can do my substitution here. My volume is equal to 2 pi times the integral from 9 to 0. Notice that your limits switched because they switched here. And then my dy gets replaced with negative, sorry, this should be a u, negative du. So that way you have the negative here, and 9 minus y gets replaced with u to the 3/2. All right, so now we take the antiderivative, add 1 to 3/2 to get 5/2, and multiply by the reciprocal of 2/5. And so we simplify that and we substitute in our limits. So we have negative 4 pi over 5 times 0 to the 5/2 minus 9 to the 5/2. So basically you have a negative and a negative being multiplied, so the result is positive. And so we need to simplify 9 to the 5/2, which is the same thing as square root of 9 to the 5th power. Square root of 9 is 3. 3 to the 5th power is 243. Multiply 243 by 4 pi, and you get a volume of 972 over 5 pi. This is a much larger number than previous examples, but it's also a much larger solid that's created. The original area was much bigger than previous examples as well. All right, so now that you've learned both the disc washer method or the cylindrical shell method, it could sometimes be a little confusing as to which one you should use over another. Sometimes it's just as easy one way versus another, and other times one way creates a lot more difficulty, and sometimes one of the methods simply will not work. So here's a comment or something to keep in mind. So an easy way to remember which method to use to find the volume of a solid of a revolution is to note that the disk washer method is used if the independent variable of the function or functions and the axis of rotation is the same. So for example, if you're rotating y equals f of x around the x-axis, in that case, your function is defined in terms of x, and you're rotating around the x-axis. So then disk washer method would make sense. With the shell method, you should use that if the independent variable is different from the axis of rotation. So in other words, if your function is defined in terms of y and you're rotating around the x-axis, then that would be the most straightforward way to evaluate that volume. So here's just a little chart to help you keep that in mind. So if you rotate the region y equals f of x around the x-axis, you would want to integrate with respect to x. If you rotate a function of x with respect to the y-axis, then in this case you would the shell method would make more sense, because with shell method you would be able to leave your function in terms of x. If your function is defined in terms of y and you're rotating around the y-axis, well then again disk or washer, if there's more than one function, would be the best choice. And if your function is defined in terms of y and you're rotating around the x-axis, then in this case the shell method would make more sense. So with experience you will get better at this, but for now try doing the homework. Good luck.